Forces of nature. There are four forces. You'll be familiar with the force of gravity. It's what holds us on Earth. You'll also be familiar with electrostatic forces between charged objects, attractive when the objects carry opposite charges, repulsive when they have the same charge. And you'll also be familiar with magnetic forces. Well, James Clerk Maxwell found that electrostatic and magnetic forces were actually the same force, called the electromagnetic force. There's also the strong force that acts between quarks, and this is responsible for holding the nucleus together. Otherwise, the electrostatic repulsion of all the positive protons would not allow this. And finally, there's the weak nuclear force. This is responsible for beta decay. It is believed that these forces come about through the exchange of particles, and here I'm going to show you how an exchange of a particle can lead to a force. We have two ice skaters facing each other, one holding a ball which he will throw to the other, and this is what will happen. Both ice skaters felt a force away from the other, the first one by throwing the ball, the second by catching the ball. So the exchange of the ball has seemed to lead to a repulsive force between the two skaters. So that was the exchange of a particle leading to repulsion. Now to look at how exchange of a particle could lead to attraction. In this case, the skaters face away from each other, and one holds a boomerang. If he now throws the boomerang like this, the exchange of the boomerang has led to attraction between the two skaters. The exchange of a particle leading to attraction. So what about the exchange particles involved with these four forces of nature? Well, they cannot be detected, otherwise they would not do their job. In a similar way, if somebody had run onto the skating rink and caught the ball mid-flight, it would not have affected the second skater. For this reason they're called virtual particles. The more mass they have, the easier they would be to detect, and therefore they must have a shorter range to avoid detection. Now to look at the four forces and their exchange particles in more detail. I've listed the forces here in order of their strength. The strong force, as the name suggests, is by far the strongest, and gravity, as may surprise you, very much the weakest. The exchange particle for the strong force are gluons. These are pions or pi mesons. Their range around about 10 to the minus 15 of a meter, roughly the size of a nucleus. I've given these relative strength of 1. We'll compare the others with the strong force. The effect of the strong force is to hold the quarks and nucleons together against the electromagnetic repulsion which would occur between the positive protons in the nucleus. So basically it holds the nucleus together. The electromagnetic force has photons as its exchange particle. As these have zero mass, they can have infinite range. Electromagnetic forces are roughly 100 times weaker than the strong force, and it is these forces which act between charged particles. The weak nuclear force has W+, W-, and Z0 bosons as its exchange particles. These have a relatively high mass, and so a tiny range, 10 to the minus 18 of a meter, roughly 1/100th the diameter of a proton or neutron. They are roughly 1,000,000 times weaker than the strong force, and it is the weak nuclear force which is responsible for beta decay. The ejection of a W boson will change quark flavor, changing a down quark to an up quark in beta minus decay. This W boson will then decay into the beta particle and the electron antineutrino. Finally, gravity, with the suggested exchange particles of gravitons, though these have not yet been detected. Gravitons have zero mass and therefore infinite range, and a tiny strength of 10 to the minus 40 times that of the strong force. The reason we're so familiar with gravity is it is always attractive, so a large mass, like the Earth, can produce a strong gravitational field. The effect is between objects with mass, and as I've said, it is always attractive.